Hello. So we're going to take a break from integrals in the meantime. And in the next few videos, in this next section of the course, we'll be talking about objects called sequences and series. And you'll see them at the beginning and you'll probably think, well, this is like completely different from what I expected when I was signing up for this calculus course. But you'll see towards the end how all the ideas that you've seen since your differential calculus course actually come together quite nicely when we get to the end of these topics here. And so I'm just going to talk about our goals here for this section. And this is pretty much what we're going to do here. We're going to try to describe the behavior of infinite lists of numbers, right? And sure, that may seem like a bit intimidating to you, right? For sure, you know lists of numbers, but infinite lists of numbers? What does that even mean? Can we talk about them in a systematic way? And the second point probably raises some questions for you as well. What does it mean? Describe functions as infinite lists of numbers. Can we even do that for functions? How do these infinite sequences help us talk about functions? So before we get to all of that, let's first define, let's start from the very beginning, let's define what sequences are. And a sequence is, well, pretty much an infinite list of numbers, right? But we're going to use notation that looks like this, a sub n, to denote that it's a list of numbers where the first term is called a sub 1, right, with a subscript 1. The second term in your list of numbers is a sub 2, and so on, right? You have a third term, the nth term has a sub n, and this list goes on forever. Now, probably the simplest example here, or the one that's most intuitive for you, is just the list of natural numbers or counting numbers, right? You start listing them: 1, 2, 3, 4, 5, and so on. And so in this case, 1 is a1 in the sequence, 2, the second term, is a2, 3 is a3, and so on. And for this particular example, for the naturals, we're actually able to describe this using a general formula for the nth term. What's the nth term in this list? So the first term is 1, the second term is 2, and so on. Well, the pattern holds forever. So the nth term must be exactly equal to n. In other words, we can describe the natural numbers as the sequence from n equals 1 to infinity, given by the formula a sub n is equal to n. In other words, the nth term is n. And I'm going to note a couple of things here. First, note that we can't skip numbers. Right? We can't skip terms. So you can't have a sequence that goes a1, a2, and then a4, for instance, right? The third number, that's going to be your a3. Now you can actually start your sequence somewhere else. Like sometimes we may have a sequence that starts at 0, and that's fine, right? But once you start a sequence, you have to keep incrementing this index by 1 each time. Also, there are no fractional indices. So it doesn't make sense for us to talk about, say, a sub 3/2. Right? There's just no 3/2 term here. Right? So it's only going to be indexed by integers. Okay, so let's look at a few more examples. So the first example is what we just did here. This is this sequence of natural numbers given by the formula a sub n equals n. The second sequence here, is there a formula for it? There's not, actually, because this is just described by saying a sub n is equal to the nth prime number, for which there is no known closed form formula in terms of n. I mean, that's still a sequence though, right? Even if we don't have an explicit formula to compute whatever number the nth term is. But here we would say a sub 1 is 2, a sub 2 is 3, a sub 3 is 5, and so on. Okay, now sometimes we will give you the formula, right? Sometimes you'll be given the formula for your sequence, like a sub n equals n over n plus 1. So here your sequence is going to look like this. Well, you plug in 1 and you get 1 over 2. You plug in 2 and you get 2 over 3, and so on. And that's what this sequence looks like. And it's, again, it goes on forever. And finally, you can have something like this with a trig function. If it doesn't say where it begins, like in here, then you can just assume it starts at n equals 1. So a1 equals sine of pi, which is 0. a2 equals sine of 2 pi, which is 0. And in fact, for any integer, sine of n pi is 0. So this is just a sequence of all zeros. Right? Not that interesting, but an infinite list of numbers nonetheless. Right? So you are allowed to repeat numbers in here. Right? The numbers in your sequence, they don't have to be distinct. And so why don't you try these out for yourself? Right? Pause the video now and try to find a general formula for a sub n. Okay, did you try it? What is a sub n for these sequences? Well, let's look at what's happening here. In the first sequence, in part A, we're starting with 19. That's a1. a2 is 22. a3 is 25. And you'll notice that each time we increase the index by 1, right, from term to term, what we're doing to the number here is we're adding 3. And so a sub n is going to be equal to what? Well, you're starting with 19, and you're adding 3 n minus 1 times to get to an. So that's your general formula, and you can check that it works here. How about part B? Well, it's kind of similar. Notice a pattern here from term to term. a3 equals 8 over 3, a4 equals 16 over 9. And now what you can notice is, from term to term, you're actually multiplying by 2/3. And so what's an? Well, we started with 6. And then we're multiplying by 2/3, n minus 1 times to get to an. So there's a power of n minus 1. Right? And these two sequences are called arithmetic and geometric sequences. Arithmetic because there's a common term that you're adding to each one to get to the next. So you're adding the same thing throughout from term to term. Here, for the geometric sequence, you're multiplying the same thing throughout to get to the next term. Okay, so that was fun, right? And these examples were not that difficult, just needed to find a pattern. Sometimes you'll get a sequence where it's not immediately obvious, right, what the general formula is, right? But that's not going to happen too often in this course. Usually for the analysis that we'll be doing, you'll actually be given these formulas, like this one, n over n plus 1. We already saw this in one of the previous slides, right? This was 1/2, 2/3, 3 over 4, 4 over 5, and so on. And what I just want to do here is to give you a way to visualize these sequences, right? Because another way of thinking about sequences is when we say an equals n over n plus 1, right, where n is an integer, or let's just say natural number for now, really you can think of this as a function where you're inputting an n, right, giving n as an input, and the formula tells you what the output is. So another way to think about sequences is as a function from the naturals to the reals, where f evaluated at n gives you, in this case, n over n plus 1. And so functions have graphs, right? The graph of a function is just all points x comma y such that it satisfies f of x equals y. Only in this case, your x's, right, your domain, is only the natural numbers. So you're not going to get a curve that looks like this, that's unbroken. You're going to get discrete points on the plane, right? So let's do it here. A sub 1 is equal to 1/2. That means that's the point 1 comma 1/2. It's about here. A sub 2 equals 2/3. So that's the point 2 comma 2/3. That's around here. And then 3 3/4. 4 and 3, 4 over 5, 5 and 5 over 6. And I want to make sure I don't go past 1 here. Right? Because how do I know that? That I'm not ever going to go past the line y equals 1. Well, n over n plus 1 is always going to be less than 1, right, for any natural number n. Also, probably more interesting, is the fact that from term to term, as n increases, you'll notice that n over n plus 1 actually gets really close to 1. Right? One easy way to see that is to just write n over n plus 1 as 1 minus 1 over n plus 1. So the difference of a sub n with 1 is this part, is 1 over n plus 1. And that goes to 0 as n grows very large. So we will actually call this a limit, similar to what you've seen before, right? In differential calculus, even when we were doing Riemann sums. So I would write limit as n goes to infinity of a sub n is equal to 1, because of the fact that your points get closer and closer to 1 without actually, well, touching 1. Well, okay, so that's false. You can actually touch your limit. In this case, it doesn't. But your points get arbitrarily close to 1. You can get as close to 1 as you'd like. as long as you take n large enough. Okay? And so, well, that's the definition of a limit. If you can make the terms a sub n as close to the number L as you'd like, as long as you take large n, then that's the notation for it. Right? So you can also say n over n plus 1 approaches 1 as n goes to infinity, using the second type here of notation. And in this case, we're going to say the sequence converges or is convergent. If it doesn't have a limit, you're going to say the sequence diverges or is divergent. Right, so I'm going to give you a few other examples here. We saw a while ago the sequence of zeros, right? When we had sine of n times pi, for any n integer that you plug in there, it's just going to give you a 0. So in this case, limit as n goes to infinity of an is equal to 0. All the terms are 0, right? So all the terms are close to 0 because they're all 0. So we would say that this is a convergent sequence. But how about this sequence? 1 minus 1, 1 minus 1, 1 minus 1, and so on. You can draw the graph here. Right? When it's 1, then it's 1. When it's 2, it's minus 1. And it alternates. And you can probably see from the graph here that this sequence is going to be divergent. Right? You can't make it close to any number that you'd like, because infinitely many of your terms will be 1 and infinitely many of your terms will be negative 1 as n grows very large. So in the next couple of videos, we'll talk more about some of the characteristics of sequences and also ask the question, what happens when we try to add all these numbers up in your infinite list?